Hi, this is Rohan from educator.ai. Let's dive in. Attention is the engine that lets a language model relate words to each other. But one attention calculation can only track one kind of relationship at a time. In this video, we build up multi-head attention piece by piece and see why running several of these in parallel is what makes the mechanism so powerful. Consider a single sentence. To understand it, a model must track several relationships at the same time. Who is doing the action, which describing words attached to which things, and what a pronoun like it points back to. These are different questions. Forcing one attention calculation to answer all of them is like using one highlighter for a whole textbook. Here's the mental model. Rather than one reader trying to notice everything, imagine a small panel of specialists reading the same sentence. One focuses on grammar, another on what pronouns refer to, another on tone. Each reads independently. Then they combine their notes into one summary. Each specialist is what we'll call an attention head. Let's open up a single head first. A token is one chunk of text, like a word. Inside a head, every token produces three vectors by multiplying its embedding with learned weight matrices. The query says what this token is looking for. The key advertises what a token offers. And the value is the actual content it will pass along. Queries and keys decide who talks to whom. Values are what gets sent. To decide how much one token should attend to another, we take the dot product of its query with every key. A large dot product means the query and key point in similar directions, so they are relevant to each other. Look at the row for sat. Its query lines up strongly with the key for cat. These are raw scores though. They can be any size, so we can't use them directly as weights. We fix that with softmax, which turns each row of raw scores into positive weights that add up to 1. Now each token has a tidy budget of attention to spread across the others. The sat row still leans on cat, but now everything is a clean proportion. Think of it as, how much of my attention do I spend on each token? Finally, those weights are used to blend the value vectors. Each token's new representation is the weighted sum of everyone's values, with the attention weights deciding how much of each to mix in. So the output of one head, for the token sat, is mostly the value of cat, plus a little of the others. That's one head, start to finish. Score, normalize, blend. Here's the full attention pattern for one head as a heat map. Each row is a token's attention budget. This particular head has learned a subject-verb relationship. The verb, sat, pours most of its attention onto cat, the thing doing the sitting. That's useful, but it's only one kind of link. What about the pronoun and the location? A single head can't chase everything at once. Now the same sentence through a second head with its own query, key and value matrices. It has learned something completely different. Sat and on both attend to mat the place. Same words, same positions, but a new relationship surfaces. This is the key idea. Different heads specialize on different patterns, because they each have their own learned weights. In a real layer, these heads don't take turns. They all run at the same time on the same input, each with its own smaller query, key and value projections. Because they are independent, the hardware computes them in parallel. Multi-head simply means many of these attention calculations side by side, each free to learn its own relationship. So how do the specialists pool their notes? Each head outputs a smaller vector per token. We lay those outputs side by side, concatenating them into one long vector. Then a single learned matrix called the output projection mixes them back down to the original size. That final matrix lets the model decide how to weigh what each head found. The result is one vector per token, ready for the next layer. More heads means more distinct relationships a single layer can capture at once. There's a neat trade. The more heads you add, the smaller each head's dimension, so the total compute stays roughly fixed. Large models often use dozens of heads per layer, stacked across dozens of layers, which is how they track grammar, references, and meaning all together. Let's prove it with a tiny NumPy version of one head. We build queries, keys, and values by hand, take the scale dot products, apply softmax, and blend the values. Notice the printed row sums are all 1, exactly as promised, and each output vector is a weighted mix of the value rows. This is the whole mechanism in a dozen lines. Now two heads. Each gets its own random query, key and value matrices, seeded so it's deterministic, and produces its own output. We concatenate the two side by side, giving a wider vector per token, then multiply by an output matrix to project back to the original width. That's multi-head attention end-to-end. Parallel heads, concatenate, project. Two things trip people up. First, nobody programs a head to do grammar or references. Those roles emerge on their own during training, and many heads are messy or redundant. Second, combining heads is not a simple average. The concatenation keeps each head's output distinct, and the learned output matrix decides how to mix them, which is far more expressive than averaging. Here's a quick review lens. On the correct side, independent heads, each with their own projections. Softmax, giving row normalized weights. Concatenate then project with a learned matrix, and roles that emerge during training. On the risky side, sharing one set of matrices, skipping softmax, averaging heads, or assuming a head, always does one fixed job. Keep the left column in mind, and your mental model will hold up. To sum up, one head scores queries against keys, softmaxes into weights, and blends the values. Multi-head attention runs many of these in parallel, letting each specialize on a different relationship. Their outputs are concatenated and projected back down by a single learned matrix. And the more heads you have, the more relationships a layer can capture at once. That's the heart of the transformer.